Hello and welcome to day 20 of Advent of Code 2024. So this is called race condition. Just a note that this video comes out one day late because I was away yesterday. So yeah, that's the reason. So we are at day 20, so we are on the final stretch of this year's Advent of Code 2024. And the problems tend to be harder and harder at this time of year. So in this puzzle is so let's read about this. So the historians are quite pixelated again. So this time a massive black building looms over you. You're right outside the CPU. So this is kind of a reference from the 2017 day 24 actually. Version of AOC. As you probably have seen, that the calendar kind of celebrates 10-year anniversary of Advent of Code. So while the historians get to work, a nearby program sees that you're idle and challenges you to a race. Apparently, you have arrived just in time for the frequently held race condition festival. The race takes place on a particularly long and twisting code path. Programs compete to see who can finish in the fewest picoseconds. The winner even gets their very own mutex. So they hand you a map of the racetrack, which is also your puzzle input. So this is the example one. As they don't really give you a good comparison for the example input, I'm gonna actually work with the real input. Yeah, so that's what we're going to do. But as you can see here, when the first time I saw this, I kind of thought, okay, that this is a new shortest path problem, basically. But it is actually not that. So the map consists of a track, which is dots, and including the start position is the S and the end is the E, and the pound signs are walls. So this is a map structure we are pretty used to right now because we've done a lot of these problems already. So, but when a program runs through the racetrack, it starts at the start position. Then it's allowed to move up, down, left, and right. Each such move takes 1 picosecond. So it's kind of one picosecond per move. So it's one step. For each step, it's one step, basically. So the goal is to reach the end position as quickly as possible. So in this example racetrack, the fastest time is 84 picoseconds. So I kind of just went ahead just to check this when I first saw this problem, and yeah, there is actually only one way, because there is only a single path from the start to the end, and all the programs would go there in the same speed, so the races used to be pretty boring. So to make things more interesting, they introduced a new rule to the races. Programs are allowed to cheat. So the rules for cheating are very strict. Exactly once during a race, a program may disable collision for up to 2 picoseconds. This allows the program to pass through walls as if they were regular track. At the end of the cheat, the program must be back on normal track again, otherwise it will just receive a segmentation fault and get disqualified. So a program could complete the course in 72 picoseconds, saving 12 seconds by cheating for the 2 moves marked 1 and 2. So if it applies the cheat here, so this was a wall, and so it goes right through here. It will actually skip this entire bend here to come here, so that they will save all these steps. And if they apply the sheet here, they will kind of they will save they will go right through here, so they will save 20 picoseconds by that, and this sheet says save 38, which will be it goes right through here instead, goes up, comes back to the end. Or this sheet, which is always probably the obvious one, that will save 64 picoseconds. This will kind of get you right through the end in the quickest way possible. So each sheet has a distinct start position, the position where the sheet is activated just before the first move that is allowed to go through walls, and the end position. Sheets are uniquely identified by the start position and end position. And in this example, the total number of sheets grouped by the amount of time they save are as follows, and they kind of list this. And the final answer is how many sheets would save you at least 100 picoseconds. So let's go into the code, because as I said before, this is really not a regular pathfinding problem, but it's kind of a pathfinding problem, so to say. So in our code, we obviously will grab our grid. So I'm gonna actually, so that this video doesn't go on for too long, I will actually kind of copy the code in and just kind of comment along the way. So we will as normal, we will bring in our rows and columns, and we will have our current row and current column. This will actually be just a reference point, because we will begin by going to the grid and finding our starting position, because that will be our kind of base point of exploration, so to speak. And we also need to apply this little thing as well, because when it kind of breaks here, it will come here, and we will kind of increment the row once more, so we need to deduct the row here. Yeah. So the first thing we need to do is actually calculating the distances in this grid. So we will calculate every type of distance in the grid, and we will have a method for this. This will more or less be well, not really a pathfinding. Well, in some sense it will be a pathfinding exploration kind of method, but yeah, we're gonna actually look at it. So just let me bring in the code here. Copilot seems to think we need to have this, but it's not completely. Well, it is actually more or less what my code looks like. Not actually, not really. We will take it step by step here. Yeah, so we will create kind of a distances array, which will be our row and col. Will be number rows and cols. So we will kind of build up that dimension. So we begin by setting all these distances to -1, because now we're about to kind of measure the distances between two these, and it's actually the distance from the starting position to that distance actually. But in this method, we kind of sending in our current row and current column. I realize I we could have probably named this variable some bit more clear, but I'm just kind of going by the code I created, and I haven't actually had time to make it totally clear yet. So we begin by setting the distance to our current row and current column, which will be our starting position. So that will be 0, of course, because that's at our start, and then we will kind of do this. So we will have. So while current row and current column will, that's basically why we're calling that, because these will kind of be updated once when we move through our grid. So we will kind of do this until we reach the end, and we will use our normal direction markers. So it will be direction column and direction row and direction column, which will go down and up and right and left. So we will kind of do the normal way. We will set a new row, new column, check if we are in bounds, check if we are not in a wall, check that if this distance has already been visited, meaning that it's not -1, then we will also continue. And when we have if we pass all these checks, we will set the distances of this row and column to the distance from the previous distance +1. So we will kind of build our distances onward. So basically, we can just quickly draw this. So let's say that we have this kind of path here. Oh, so we have dot. Oh, there should not be a dot here, of course, because yeah. My drawing is actually very, very bad, but yeah, and oh, you get the picture here. So let's say that this is our starting point. So we begin by going here. Well, we will not be 10, so we will check here. Then we will measure where that will be 1. Then we will go from there to the next, and that will be 2, because it will be what the previous one +1, and we will go that way basically. So we will go back. Let's move back here. Yeah, so that will be, and in the end we will have kind of all our distances from the yeah. I don't know, it seems like we have a breakpoint there. Yeah. So we will first calculate those distances, because that will be our kind of baseline for doing the next thing, which will be finding all these sheet points. So the distances will kind of be the row and column and the distance from the start to that position. So our sheet count method would be kind of our other where we actually do the work we should do. So we will have our kind of we will have our sheet count, and so we will do this in a sort of a loop. So we will basically do the for each row in rows, or for the current row where current row is less than row. So we will loop through the rows, and we will also go through the columns. We will have we will do, not exactly, but I mean, Copilot seems to think it knows exactly what I'm going to do. Yeah, so in this loop we will have our kind of a base checks. So we will always check if the current column is a wall, then we will just move on to the next. Then what we will do is I will actually just copy this entire thing here so that we can more easily talk about it. So here we will, what we're doing here actually, so this is more the specialized thing, because we're actually checking in kind of a what we do is we go two rows up, then we go one row up and one to the right. We go two steps to the right, or one row down and one to the right. So this will kind of only be half of the directions, but as we are doing an absolute distance, we don't need to check every other diagonal direction. So basically it's like, let me get rid of this. So basically we will kind of if we have our point here, we would kind of check 2 rows up, we would go there, we would kind of go there, we would kind of go there, and we will also go there. So that's basically what we're checking, all these directions. And what we're doing here is, the basic sanity check here, that that we are still within the bounds of the grid, and also that the grid that the char is not because one of the rules said that after the sheet you can't be inside a wall, because that's not, you must be on a regular track when the sheet ends, and that the sheet end position will be that new row and new column, so that we need to check that. And as a last thing we do here is that we calculate the absolute the absolute distance between the previous row and the we do a kind of a Manhattan distance here, and we check that this would be greater or equal to 102, and that what we have 102 is kind of we should it said 100 picoseconds, but we also need to add 2 because we are kind of moving 2 steps by the sheet. So that's why we do it like that. And if that happens, we increment our sheet count. And really, the only thing that's left is to return the sheet count. So that way we will find all the available sheets we have in our grid. And by doing that, we will have our part 1 answer. So yeah, so this should get our part 1, and remember now that I'm actually using using the real input, and that and my answer is 1389, so that's what we are aiming for. So let's run this. Yeah, we have 1389 here as our result. So that's part 1. It's not that complicated actually. So let's go back and look at part 2 then. And part 2 here for this problem is not that big of a thing actually, but it is a bit more complicated. So the program seems perplexed by your list of sheets. Apparently the 2 picosecond sheeting rule was deprecated several milliseconds ago. So the latest version of the sheeting rule permits a single sheet that instead lasts at most 20 picoseconds. So now, in addition to all the sheets that were possible in just 2 picoseconds, many more sheets are possible. This 6 picosecond sheet saves 76 picoseconds. So now they can move up to 20 picoseconds in a sheet, and that kind of complicates things some, but not that much. One important rule is like we see here for these 2 sheets here. So it says because this sheet has the same start and end position as the one above, it's the same sheet, even though the path taken during the sheet is different. So we start at this position, we go 6 picoseconds, and we do the same amount of steps for this. We will end up in the exact same place. So if a sheet has the same start and end position, it will be the same sheet even though their paths will be different. And also the sheets don't need to use all 20 picoseconds. Sheets can last any amount of time up to and including 20 picoseconds, but can still only end when the program is on a normal track. So that's the same rule. And any sheet time not used is lost, and it can be saved for another sheet later. So you still need a list of the best sheets, yeah. So the thing here is that I mean the important thing here to note is this is one important thing. Also that any sheet time not used is lost. So that you don't need to actually find a sheet that lasts entire, and you don't have any sheet time left after you find a sheet. So we will still be checking the sheets basically the same way, but now we're kind of going a lot further out from our current position. So let's go back to our code here. So the thing we're actually going to do is we're actually going to expand our method a bit, and so we're going to now kind of add at a boolean. So if this is the new sheet length, then we're going to do things a little bit differently. We will also have, basically, because of this rule that we can have the same sheet for different for if it has the same start position and same start and end positions, it will be basically it will be considered the same in the end. So that's why I'm kind of storing these in a dictionary, so that I can kind of easily get the distinct ones at the end. So we will kind of do like this here, so that we will have an if not new sheet length, we will still do our part 1 thing, and otherwise we will do our part 2 thing. Yeah. So in this sense, we need to kind of we kind of need to build some kind of radius around our position. And also when calculating this, we will not use the absolute distance calculation. We will actually do yeah, basically it's more or less like that, but yeah, we will kind of do this in steps instead. So we will build kind of a radius around our position, which will be from 2, because the 2 is what we found here. So it will be from 2 up including 20. And then we will do an inner loop that we will check all these kind of we will do our inner loop here, where we will be checking all these steps kind of out from our position. So our kind of direction row will be from 0 up until and including the radius. So we will start by 0 going up to the and the radius will kind of start with 2. So first we will check 0, 1, and 2, and then will be 3, and so forth. And the direction column will be our radius minus the direction row. So we can actually just paste in the whole thing here. We can talk about it, and it's not yeah. So when we're inside in this inner loop, we will check our new, yeah. My naming has been kind of skewed because I'm using those regular names that I used to have. That I always used to use. So I need to have new names within here. So yeah, obviously if you want to kind of copy this code yourself, you don't need to use these names. You can use more descriptive names, but I kind of like to have this short and sweet, so to say. Yeah. So the direction row and direction column here will be kind of our DRDC, and it will be dr minus dc, which will be kind of going left. We will go up. So we will remain, go left, go up, and go both minus minus. So it will be kind of positive, 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 negative, negative, positive, negative, negative. So that's how we're going to actually go in those directions. So this will be normal, more or less like up here. We will check that we are in bounds, that we're not in a wall, and now we will not check if we will not do an absolute calculation of this distance. And now we also need to say that we are greater than equals to 100 plus the radius, because the radius will kind of increase. So we kind of need to be that needs to be within our calculation. And and then we check our dictionary, and we kind of add this distance to that kind of starting position and ending position of this sheet. And in the end here, we need to have we need to return. We kind of will update this. So we need to for part 1 we must return that count, but for part 2 here, and this was actually something I struggled with, because I kind of knew that I had the correct solution, but I didn't actually know how to actually do this. So the thing is, basically what we or actually, yeah, let's just run this and see, because I maybe this is actually wrong, because I'm pretty certain that I did this another way. Let's just check here. Okay, that's oh, something's happening. Why is it not? Let's just switch to release, just to get it working. Oh, okay. Yeah, I'm going to just. Yeah, okay. Yeah, I need to actually restart my Visual Studio environment here, because it was totally. Yeah, it was not working properly for some reason. So let's just run this now and see, because I actually want to show you this, that the kind of length. Yeah, well, that's the first time now we have something in here. So now we have our entire bit. But what I actually found out here is that either if you do only counting the keys, or counting the distinct values of the values, you will get the same answer. So either way, actually. So we can just do kind of this instead, if you want. You can say the keys count will be, and if we do that, we will kind of have the same answer. So, and if we double check this, it will be so it's 150.68, and that's I think what we get. 150.68, yeah. So this is kind of the answer. Now I actually saw that in my code I actually kept it like, because this is kind of an easier way to do it, and then I can just doing distinct over the values. And basically this is also why I kind of do it this way, because just update. I tried first to use the normal sheet counter just to update that one for each of these distances, but it didn't got me the right answer. So then I kind of took a note of that different sheets could be considered the same as long as their start and end positions are the same. So that's why I kind of organized this in dictionary. We don't use the dictionary for anything other than to get our distinct kind of values from. So yeah, so this was my solution for part 20 or for day 20, and let's get back to our. So it will probably be a little bit. The videos will come out little bit later now, because in the days leading up to Christmas we have a lot of other things to do here, and yeah, so I will probably not have time to do the videos every day, but I will have all the days eventually. So today I was actually completed day 21 of Walktrough code, but it was a very hard problem today, and I have not yet finalized my code to be pushed into the GitHub, and also the performance of my code right now is really bad, so I have to fix that before I can actually do a video about it. I need to fix that so it will kind of work as a kind of a generic solver kind of thing. So let's check back on day 21. I will probably publish that video tomorrow hopefully, if I can get my own version fixed in a proper way. And yeah, so maybe the day 2022 will not be that hard as this one was. So it will be kind of, I will probably do day 20, 21 and 22 at the same time basically. And yeah, so let's see what comes next here. So bye bye.